Alrighty, let's see what we got here. Okay, maximum matching of the players with trainers. I didn't finish yesterday's issue with the hard problem with the min and max rounds for pairing two people in the tournament. It is on the docket amongst other incomplete hard problems that I've faced recently. It's just sad state of affairs. Anyways, maximum matching of players with trainers. Medium, maybe done this previously. We'll see. You're given 0 indexed integer array players, where players of I represents the ability of I player. You're given a 0 indexed integer array of trainers, where trainers of J represents the train passive J trainer. The ith player can match with the jth trainer if the player's ability is less than or equal to the trainer's training capacity. Additionally, the ith player can be matched with at most one trainer, and the jth trainer can be matched with at most one player. Return the maximum number of matchings between players and trainers that satisfies the conditions. Okay. 479, trainers are 8258. Players can match with a trainer that is less than or equal to trainer's ability. Okay. So like the 4 and 7 can match with the 8 and 5. So 2 players. The player with 9 can't be trained. 1, 1, 1, 10. One of the ones can be matched with the 10. Okay, I think this is medium. Seems straightforward, maybe easy. It seems like I might be able to just use 2 pointers after I sort them. Sort the players and trainers. Seems like it should be doable, like a greedy approach. So if I sort this, right, if I make this 479 and this be 2588, it should be like I go through, or maybe go reverse order here. The ideal pairing would be like if 4 would match with the 4 here, so I would just go down 4 match with the 5, and then 7 would match with the 8. 2 can match with anything, so like remove from the consideration anything that is a trainer that's smaller than the current player. And it's like a greedy approach, so any pairing that you can work where you have the smallest possible trainer above the player, then that's like just the ideal allocation of that resource. So I think this should just be like 2 pointers maybe. Okay, so players dot sort, trainers dot sort, and then I'll say p index or pin is going to be 0, and tin for t index is going to be 0. Player index, that's why I call these weird names, of course. Trainer index. And there's probably going to be a better way of doing this, but I'll say just while the pin index is less than the number of players, let's say n players is going to be equal to the length of players. N trainers is equal to length of trainers. While pin is less than the number of players, and 10 is less than the number of trainers. So kind of the ideal scenario is I need to go down the list of trainers until I see one that is bigger than the current player. So while 10 is less than n trainers, and the trainer power of this index is smaller than the player power. Players at this pin, then it cannot be done, so just skip on to the next trainer index. At this point, it should be like something like if 10 is not equal to the number of trainers, then this should be valid. So we'll make the assignment here. Valid. Trainer is okay with player. So it should be something like answer increment by 1, player index increment by 1, trainer index increment by 1. And then that should be it. Yeah. The fact that there's kind of redundant conditions in these if and while loops, if statements and while loops is, I'm going to try to fix that, or try to find a way around that. But now this is the most straightforward logic I can think of. Okay. So the normal thing that I would do to kind of prevent this out of bounds issue of indexing is have a dummy value that kind of what's the word I'm looking for? A dummy value added to the array that backends it so that it doesn't kind of overflow over it. So how would I have set up here? The other thing I can do is just have a while true loop and then have a break. So what would prevent it from being just while true? I need to go to the very end. And I could have a player that is impossible to be assigned. I could have a player that's impossible for you to be assigned. Does that make sense? So if I wanted to, I think the thing I want to get rid of is this condition for the most part. So if I have a so if I add a dummy trainer that has infinite power, then infinite training capacity, then the index for that trainer would always be doable, or that trainer would always be assignable to a player. Then it wouldn't stop it from going to the next trainer index. So what would stop it? So I think it would stop it if the trainer was not less than. No. If the trainer is not less than, then it would not do this loop, but then it would still move on to the next index here. Okay, I think maybe I have a break here, a statement that breaks if the index is equal to the number of trainers. So if it's not equal to the number of trainers, maybe I should have a break here. Actually, I can have it like this. If the index is equal to the number of trainers, then break. The indentation here is slightly better in my eyes. Actually, I can't do a while else loop. I guess I can't do it. Is there a while else loop? I think you can do while else's. In Python, a while loop can optionally have an else block associated. I think this actually works here. I think I can do an else if in a while loop. Okay, can I do this? Well, yeah, I can probably do this if I first spell it correctly. This is the actual first time I've ever done a while else. It makes sense that it should be possible, or makes sense to be logically. Okay, so still don't feel great about this. How do I set it up so that this thing doesn't hit? So if I set up a dummy player, well, the dummy player has this kind of infinite power, so therefore it wouldn't be able to have a trainer that has capacity for them. Then it's not going to go out of bounds. Not going to go out of bounds. While trainer's capacity is smaller than the player's capacity. Stop. While trainer's capacity is smaller than the player's capacity, keep on moving. Move on to the next one. As long as there is a next trainer. Number of players is player index. That's the number of players. I wonder if that's actually, if I use sorting, if it goes faster actually to find the index. Yeah, actually. So if I try to use linear instead of going linearly down the list, if I try to find the index. So for instance, if the players are 479 and the trainers are 2588, I might be able to find where you insert 4. Yeah, so if I find where the 4 is inserted here, the index that 4 would be inserted would be index 1, and the trainer at that index should be bigger than that number. So therefore I can say that that trainer should be assigned with that player. And then with using bisect left to find that index. And then I can have the next bisect left call be using the indices that are after it. Okay, so I think this is as far as I'm going to go with this technique. I'll go try to use the bisect to find the indexing. So the other one would still, I think, this is kind of a linear approach. Linear approach to finding the smallest, finding the kind of best fit trainer, which is the first unassigned trainer that is greater than or equal to player power. So this is going to be more of a search approach, a binary search approach to finding the best fit pair. So I think everything before this is fine, while the player index is less than num players, trainer index is less than num trainers. I wonder if I need the second conditional, to be honest, because it's not going to be necessary on the first loop. This conditional, yeah, it just doesn't, it's not necessary. Because you're immediately going to check the condition in this while loop here. If the condition fails here, then it just breaks. And then it does the next iteration. Well, actually, so let me double check if this change works. I mean, it's a marginal improvement at all, but it is a slight removal of the redundancy and random variation for that. Makes it worse, but it's fine. So what am I looking for here? I'm going to say that the trainer index is equal to the bisect left of the array, trainers array, looking for the value that is the player power here, which players at pin, starting at, it's going to look a little weird, but starting at the current index or trainer index. So current player index plus 1, or is it just current? I think it might be plus 1, because it doesn't want to use 0. If it's later on in the process, it doesn't want to use the same index. So I think it's plus 1, in which case this thing needs to start at -1. That's going to break this thing if I comment out this. It's going to break the linear approach if I comment out this one. Actually, before I forget that, I'm just going to make that here. That to the number of trainers. What's the last valid index? Yeah, I think it's probably n trainers. And then I say if that index does not equal the num trainers, so that means there is a possibility, then answer plus equals 1. N plus equals 1. Else return answer. No, sorry. Else break. Return answer here. Okay, I think maybe this might actually work immediately. All right, I cooked a little too hard. So yeah, I mean, in theory, this if you had a large enough sample, it might make sense to do this binary search approach. I mean, in theory, this can definitely have cases where this is strictly better. Like if it's, I guess it has to be a player array that is considerably smaller than trainer array, so that when you come to a player, right, let's say there's 479, and the list of trainers like was in the millions, and there was like a whole bunch of trainers that were 0, 1, 2, 3, like hundreds of thousands of them, and then you're trying to find the needle in the haystack where you find the first fourth trainer to assign this player to, the first trainer with the class C4. And then like you try to skip over a bunch of other 4s, 5s, 6s, like hundreds of thousands of them, find the next trainer that is 7. So binary search in that sense would be faster. Okay, this is okay. Too slow. In theory, can be faster if n players is much less than the number of trainers. In practice, not good. All right, lesson learned. I'll just put it down here just for reference. This thing does require that the trainer index starts at -1. Okay. So going back to the linear approach, I guess. Oh, but the bisect left is something that I definitely didn't get to until later on. Generally when I need to previously search using binary search, it was like using I don't know, a self-created helper function, or I guess you can do a while loop for it too. But bisect left is just very useful. Just finding where a certain element it would be inserted into binary assorted array using binary search, which is kind of equivalent, it's almost equivalent to searching for an element. It's not quite, because in a search for the element, you might return -1 if the index isn't found. This one, it just finds the closest element that is bigger than it, I guess. Yeah, closest the index of the element that is as equal to or bigger than the value that is given, and it would return 0 if it's smaller than the smallest value, or the size of the array, which is after the index after the last value, if it's bigger than the biggest element in this array. Anyways, very useful. You have to do some other stuff for if you want to insert at the end of the list of duplicates, or if you're trying to find an element that isn't necessarily there, you just have to do some extra checks. But basic call is this one. The basic call being the array, the value, your starting index, optionally your starting index and end index of the amount the area of the array that you want to search. And that's why I have this as the trainer index plus 1, where the trainer index is kind of just kind of where you want to start, which changes based on the previous trainer that was found. So while pin is less than number pairs, I mean, in theory you can say if you after you increase the pin here, player index, you can say if the pin is equal to the number of trainers. And the pin is less than number of pairs, while the trainer index is less than the number of trainers. And trainers I think maybe if I just said okay, I think I understand where it would normally put a dummy case. I think the dummy case would be in fact the trainer is going to append an infinite trainer at the end. And so in that case, you can just use the condition trainers is less, the trainer power is less than the player power, increment the index, and then this should always be false for the last trainer, because the last trainer should have the ability to train whatever the largest player might be. This is infinite less than some finite player power. So this is going to be false, and so this is going to stop here, and so it'll be else. Actually, I don't know why there's an else here. It should be an if statement. That's just too fancy. Okay, and if the trainer index is just if trainer power trainers at this index is equal to infinite and break. So that removes one condition from the while loop. Okay, this is dummy trainer. 2 is breaking loop. Alright, so this seems like there's a faster way of doing this. Escapes my imagination. Alright, let's spin roughly 80 something percent each time. And I think I'm good. Do you have to? Yeah, you pretty much have to sort. And I don't think it makes sense to sort. Does it make sense to sort? Is it any more sensible to sort in descending versus ascending order? If you sort using descending order, then you still would need to have a trainer that has higher power than the player. Yeah. I guess maybe you can start with a search here rather than starting at the first index. I'm kind of afraid of searching anything now that this thing is so poorly performing. Right, let's look at one last thing, which is says 10 to the 5th is the number of players and trainers. Yeah, I mean, theory. In theory, what? So while the number of players, while player index is less than the number of players. And then if you ever get to the end of the number of trainers, then you stop. Otherwise, you can keep on going to the end of the trainers. Okay, I think that's pretty much it. Alright, let's just do summary here. So this one, this one seemed as easy as some of the harder easies, or this is on the very fast side of all the mediums. Most of the time spent trying to find some stupid optimizations that I never found. So summary is, this is definitely something called, I'd classify this as a greedy approach. Greedy approach, find the first kind of minimally acceptable trainer, basically where the trainer power is greater than or equal to player power, and assign to that. So in general, you need to first sort both arrays, and then use 2 pointers to iterate over the player and trainer arrays. I call those pin and tin, or player index and trainer index. At any time within loop. And this could be even something like a for while true loop that kind of stops when not necessary. First, have a nested loop, which increments the trainer index until a minimally acceptable trainer is found. Basically, where the trainer at the tin index is greater than or equal to players at the pin index. And then assign, basically increment increment the indices, and then and count increment answer. Within loop, break loop when indices reach end of arrays. No more trainers or players. And here, slight optimization to use kind of dummy values to bookend arrays, to possibly not need as many conditionals in the statements. So yeah, so it would be something like adding a dummy trainer. So you don't need to check for the indexing of the trainer index to be out of bounds when you increment here. You just check whether or not after, because a dummy value would automatically be false for this condition in the while loop, your default condition in the while loop. But then you have to check that dummy is reached. And if that dummy is reached, then you have to break the loop, obviously. I mean, the dummy thing is a special case for the end state. Okay, time complexity, this can be O of n log n, as actually this is greedy approach with 2 pointers. This is that type of algorithm. Those descriptors on the O of n log n necessary to sort arrays, where n is basically the size of arrays. I guess this would be considered more like max of either. And O of n for the 2 pointer loops that count the actual assignment. So even though it's a nested loop, there's a nested loop portion within here. Like while pin is less than n players, while tin is less than, in practice, what would happen would be you're gonna at most run this thing. You're gonna most increment 10 the number of trainers, and you're gonna increment 10 the number of players. So it's kind of linear to those values. So it's O of n for linear. And then in theory, I wonder how I'd describe the binary search approach. I guess the binary search approach would be at most or at worst O of n, because when you're doing the is that true? It's a kind of a weird. Yeah, binary search is kind of weird here. In theory, could be better. It could also be worse in theory, because if you had a kind of a worst case scenario where you have maybe players 1 to 1,000 and trainers 1 to 1,000, like you're finding one, not linearly, you're not going down the line, but you're finding one through a binary search, which would take log n time, whereas linear would take like constant almost. Nothing broader connected that one up. In theory worse, in theory better. Theory possibly worse, in theory possibly better. Space complexity, this is going to be O of 1. I don't think I would need anything like O of 1 to as no extra space is needed. The sorts were in place. And yep. And that is that.